So hello everyone, I am Abhinav. I am a JRF at IIT Indore, working in the group of Narendranath Patra. So today I'm going to talk about GARUDA with TraP. We're looking for LPTs in or any transients in general in the GMRT archive. So this project is a collaboration between our lab in IIT Indore and NCRA with the group of Jayanta. So, um, so Manisha already talked a lot about LPTs, so I'm briefly going to give a background and just breeze through all this. So LPTs are a new class of objects, and these are all the radio transients we already know of. And they are new class of objects recently discovered, first in 2022, with periods in minutes or hours, long period transients. So here you can see a P versus P dot plot, and this is the neutron star zoo. So here are usually where neutron stars lie. And the gray region is basically the death zone, essentially, where radio emission from neutron stars, periodic emission is not um, theorized to be able to be detectable. So, but LPTs kind of challenge our understanding of these processes. So they all lie in the death zone. And this plot also Manisha showed. So this is basically the difference between coherent and incoherent emitters in radio transients. FRBs lie here, pulsars, X-ray binaries, AGNs. And in this part of the plot, there are the coherent emitters and these are the incoherent emitters. And LPTs are basically bridging the uncharted territory between them. And so what do we know about LPTs up till now? So they have periods of minutes to hours, pulse duration from seconds to minutes, highly polarized, coherent emission. They are all up till now have been detected only in the galactic plane, unknown, and no one knows exactly what the physical emission models are. Some of them are periodic, but they show variable behavior, like they emit in a time window and then they stop emitting. And some of them even have X-ray and optical counterparts. So I'll show later. So traditional searches miss LPTs because the single pulse search algorithms that in searching for transients and PA beam data, they are geared towards more much shorter time scales. And LPTs, as you know, the periods are much higher than that. There's also the thing about observational limitations. If a source has a period of 40 minutes and the observation only goes on for that part of the sky is only covered for half an hour, then you can easily miss that source. And sometimes the sources can be flagged as even as RFI because they're extremely bright most of the times. And so how do we, what do we do? We need a new kind of technique to detect new LPT, these kind of sources. So one way is to use imaging. In image plane searches, it's much easier to localize the source in the sky. And, and you can even look for the LPTs in archival data, and that solves the observational time problem. So just a brief background, this is the first LPT ever discovered. This was this Lean XJ16 18-minute period. It was actually discovered by MWA, and they saw bursts in going back 2 months in the archival data. And this source, extremely interesting, JPM J1839. Period is 21 minutes. Pulse duration is 30 seconds, 300 seconds. This source actually has been active since 1980s, and they actually found exactly this source in the archives of many different telescopes, including VLA, GMRT, and many telescopes. So this means that sources like these are just sitting there waiting to be found. It's a very good opportunity to look for them in the archive, in the interferometric archives. So GMRT has more than 20 years of data in the archive. So what we have, we have undertaken is a project to kind of look for LPTs or any transient sources by imaging data in the interferometric archive of GMRT. So for this, our lab at IIT Indore have made this pipeline. It's called GARUDA. And GARUDA is a standard data reduction pipeline we have designed for GMRT, written in Python. It's highly modular, uses CASA modules. CASA modules are parallelized and scalable processing. So undertaking a big server project like this on archival data, you need an algorithm, you need an RFI detection algorithm which is robust to many different kinds of observations and different kinds of data, bands and data. So for this, Garuda has a deep learning based flagging module. It's called GNet. So what is GNet? GNet is a unit-based segmentation model. We have tweaked the architecture of unit and trained it on data we generated ourselves. It's the advantages of using a deep learning-based RFI detection model are essentially it's ease of use mostly. That is the most important advantage. So statistical methods like sum threshold that is used in AO flagger, they are very accurate, but they have a lot of tunable parameters. GNet only has 2 parameters. Statistical methods, they are not exactly reliable with data more than 50% corruption. GNet has been trained and tested on data with more than 80% corruption, even on GMRT band 2 data. And the trade-off is speed. Flaggers like AO flagger are an order of magnitude faster. But on GPU machines, GNet can perform almost real-time flagging with a throughput of 100 GB per hour, which is more than fast enough for our use case. The imaging process and all these things take much longer than the flagging. So these are some of the, it's not very visible here, but okay. So this is the output of GNet on band 3 and band 5 data. You can see in the spectrum RFIs here, and it has removed them. And the bottom plots are not very visible. Okay, so so that's all for I'll give a brief flow of the pipeline. So this is the it takes LTA files from GMRT archives, makes it into CASA-MS files, and the standard flagging procedure. People who attended the tutorial last week will be familiar with this. And we get the calibrated data after calibration. We pass it to our flagger, machine learning based flagger, and we get the clean data. And from there, we can go to self-calibration imaging using WSLean, spectral line imaging also, TClean, Sophia. And these are the products that, data products that Garuda can provide. Continuum images, spectral views, snapshot images, and moment maps. For this project, we are particularly interested in the snapshot images. In the snapshot images of the data, we can find transient sources. So the problem now is finding transients in the, we already have good quality snapshot images. Now we have to find transients in them. So for that, we are using slow fast transients pipeline. It does image domain searches on snapshot images and makes a database and stores them there. It works quite well. And for post-processing type, the output of TraP, Kshitij and me have written this module, which is called track, transient check. And it does, so essentially TraP output can have a lot of false positives. We need to filter them out. And for that, we have devised the extra filtering methods using clustering, MAD filter, rolling median. And from there, we can crop the cubes around directed interesting sources and generate light curves and dynamic spectra as well from the interferometric data. So now I'm going to show you the workflow of the entire pipeline on how starting from LTA images and to detecting transients in them. So this is what the project is called. It's called Long Period Transients in GMRT Archival Data, LIGHT. So we give Garuda the GMRT LTA files. It processes them, calibrates, flags, images, makes snapshot images. For demonstration, I'm going to show this field. It is a supernova remnant field in which they detected this 21-minute LPT that I showed earlier. So yeah, so this image, this is the continuing image that Garuda gave. And then when the snapshot images are given to TraP, it gives us that there is an interesting source at this location. And then we just we do further filtering by using TRAC to check if it's a real source and it's not an artifact or something. And we get the light curves and the cropped cubes also. You can see the GIF of the source going. The only one pulse is shown here, this big one. And this is the GPM. This is actually the LPT that I was talking about earlier, which is detected in the archives of many telescopes, including GMRT. It's a 21-minute period. And we can also generate dynamic spectra from this observation. That was a GSB observation, actually. GAWB observations are much more sensitive, and we are extremely confident in the pipeline's ability to detect transients. So after that, we have Riptide to search for periodicity if there is enough pulses. Unfortunately, in this one, there are only 2 pulses, so we cannot do anything much about this. Actually, the Riptide output you can see here. This is the 76-second pulsar discovered by Manisha. So this is also we found in one this observation 41055 GWB observation, and you can see the pulses are clearly visible as well as the transient and the riptide output for this periodicity 76 seconds, 75.9. And yeah, so this is another interesting source. This is the 44-minute LPT. This was in this observation DDT 3341, and this was also detected extremely reliably in our pipeline. And you can see like the pulses and the dynamic spectra as well as the source. So yeah, so this is the summary. So what now? So what essentially we are doing is we are imaging the GMRT archive. We are restricting our analysis to galactic plane observations right now only, because most of the all the LPTs right now have been found only in the galactic plane. And we are detecting a lot of weird sources. Maybe we can, if someone is interested, we can talk about them later. And just to summarize my work, so LPTs are new and extremely interesting sources that challenge the understanding of neutron stars and periodic transients in the radio domain. Observational methods and observational biases, algorithmic biases make them difficult to detect. So we have made an image plane searching pipeline for GMRT, and it works really well. We already tested it on known LPTs that even Manisha even talked about, and we found them in the GMRT archive as well. And yeah, so the processing is ongoing, and let's hope next time anyone gives this talk, we have interesting sources to show. So thank you.
Hi. So my question is regarding the RFI AI-based classification. So what do you first convert it to dynamic spectra and then do you classify?
No. This is a completely okay. So this what I'm showing here is a baseline. So this is it's not very visible, but this is essentially the C4 C6 baseline in band 3. So this is interferometric data.
So for each baseline you make this 2D metric and then do, or like what kind of data set do you use?
This is visibility. This is amplitude. And in the so RFIs, you can see that they don't follow the same features as the sky signal.
Okay. So this okay, well.
So are you? Can you elaborate a little?
So this is just one baseline, right?
Yeah, this is just one baseline.
So do it for all the baselines separately?
Yeah. And we run it on each baseline. Yeah.
And they are not connected because.
No.
Okay.
Yeah.
Yeah. So very interesting talk. Have you observed any satellites?
Yeah.
Because I mean,
Yeah,
this
we
thing
have.
coming up with UEMR.
Yeah, we have actually.
Can you please elaborate on that?
I can show you some of the gifts. Maybe Jayanta also. Yeah. So we have actually observed some satellites and transient phenomena like that. Actually, essentially sources moving in the sky. And those also show up in our pipeline, but they are not that frequent. Usually, when satellites are there, they cause extremely strong RFI, which are flagged. But sometimes, satellites can scatter radiation, which can be weak, and then that gets passed down, and then it can be seen in the image plane.
Yeah. Thank you.
Excuse me. Hey, so it's really interesting about this RFI flagging method that you have mentioned. So I am curious as to how have you tried testing it and maybe benchmarking it with AO flagger? Because the advantage of having a lot of parameters in AO flagger is that you get really good accuracy with the flagging. So
you do get real good accuracy, and in general, it is also much faster. But the problem is that you have to tune the parameters for every data set. So this is so I have this slide, comparison slide. So this is AO flagger, and this is TF crop, and this is band 3 data that I showed earlier, right? AO flagger does a reasonable job, but you can see it just removes the entire top part of the band. In the lower part, it's doing a reasonable job, but not above. In GNet also has removed a lot of the up part, but some of them it's not. I mean, the overflagging problem in AO flagger is. I mean, you can obviously fix this. Someone expert in using AO flagger can tune the parameters to kind of mitigate this, but that takes a lot of time.
Yeah, so I was curious, will it not be more worth if we spend like time maybe finding a statistical method to evaluate the parameters for the AO flagger than this?
I mean, I guess so.
Because I think these issues will go if you just play around with the parameters.
Yeah, you can make this go away for this observation.
Yeah.
But what about something else?
Fine.
So this is a survey, right? This is a survey. So
you need it.
You cannot tweak it. You need to
run
continuously.
What I'm saying is you can come up with some statistical way. Yeah, we can take it up later. Yeah.
Okay. Yeah.
Hi. Very interesting work. So I was just curious about how you do beam forming from the data that you already have. I guess
we are not doing any beam. Okay, so this is completely interferometric observations.
I got it. But when you say you run Riptide, that you're running on.
We are running Riptide on this light curve. This we get from the image plane.
Okay.
This is basically just, okay, so this, what this light curve is just this thing in the middle. Just a
For
summation of
that
these
particular
pixels,
pixel. For that particular pixel,
Yeah,
right?
yeah, yeah. Pixel, the
Okay.
sum of these per pixels beam in the middle. Yeah.
Thanks, Abhinav. Let us thank
Thank you.
Yogesh. And next speaker is
Thank you.
Yogesh.